Okay, so now we have three quantities that we can measure in a simple circuit. We have voltage, we have current, and we have resistance. Now when we put these together, we have a simple formula called Ohm's Law, which is V equals IR. This is Ohm's Law. And what it says is really simply anytime we have a potential difference, we're going to get a current. Now, when we have a current flowing through a circuit, the resistance of that circuit uses up some of that current and converts it to heat. Ohm's law applies only to materials whose resistance remains constant during use, and those are things like wires, insulators, resistors. We call such materials ohmic materials. Other materials that are called non-ohmic that means that their current through that device is not directly proportional to the potential difference. An example would be something like a semiconductor device known as a diode. Three important examples of non-ohmic devices are batteries, semiconductors, and a semiconductor, we're just going to leave it at that, a semiconductor, and capacitors. These three types of materials are non-ohmic, meaning that the current through those devices is not directly proportional to the potential difference. As we go into Ohm's law, then here we're going to be dealing with only ohmic materials. Okay. So now in circuits, conductors that are designed to have a constant resistance are called resistors. Now, something that's a resistor has a specified value of resistance. Typical values range anywhere from, say, 1 ohm to 1 mega ohm. So we could get a pretty large range of resistances out of resistors. We can identify three classes of ohmic materials based on the size of their resistance. We have wires that are made of metals. Wires have very small resistivity, so they have very small resistances. And what we're going to base it, we're going to always assume then that wires in our circuits have zero resistance. Insulators, materials that are glass, plastic, air, they're have high resistances, very, very high resistances. So we won't work with them with Ohm's law. And then we have resistors, which have this kind of range of resistances, and these will be will be the ones we're working with. Here we have a picture of some resistors. Whoa, right here. Some others here. So in all the circuits examples and problems that we're going to be working with, we're going to assume the ideal wire model, which means there's zero resistance and the potential difference between the ends of the wire is zero, even if there's a current in it. Okay, so that's the ideal wire model. So when we work with resistances, we'll only be working with the resistances of the specific resistors in the circuit. One practical example then of a resistor is this toaster right here. Now the heating element in the toaster is a long wire that functions as a resistor. Current heats up the wire until it glows. Other similar resistors include the heating element in a hair dryer, the heating coil in an electric stove, the rear window defroster in a car, and a filament in a light bulb. So then the question is, we're going to move over here. When you press the lever on a toaster, a switch connects the heating wires to 120 volts. That's about 120 volts is your household circuit. The wires are initially cool in a toaster, but the current in the wires raise up the temperature until they're hot enough to glow. As the wire heats up, how does the current in the toaster change? Okay, so as our wire heats up, we want to look at what we learned last time about resistivity. So our resistivity, given to us by this right here, and we solve for resistivity, we get this. So what that's showing us is that if our area of our wire changes, then our resistivity will change. So as this wire heats up, it expands. So it increases our resistivity. So what that is, when we increase resistivity, we increase resistance. So because the potential difference stays the same across our toaster, an increasing resistance causes the current to decrease. Okay, so that should make sense because our potential difference is not going to change. The amount of potential difference coming out of the wall is 120 volts. It's not going to change. So if our resistance changes, that means then that our current changes. Remember, our resistance is changing because the resistivity is changing as the area of the wire in the toaster changes. So this ends up, the current is largest when the toaster is first turned on. Okay, so our next example says a 15 ohm resistor is connected to a 1.5 volt battery. We want to graph the potential versus distance traveled through that circuit. So to help us visualize this change in potential as charges move through the circuit, we're going to sketch this circuit right here. And so the way that I've drawn this is so that up, the direction up, corresponds to higher potential. So right here is the positive side of the battery, negative side, so our potential goes, this point's increasing up. Okay? So charges raised up through the battery and then travel downhill through our little circuit here. And so our current travels this direction, right here. This way through the resistor, this way back to the end of the battery. Okay, so what we're going to do is we're going to draw the graph then. Okay, and so here's be the graph of this. It's the distance is measured from the battery's negative terminal. So the distance S is measured from the battery's negative terminal, where the potential difference is 0. And as we move around the circuit to the starting point, the potential must return to its original value. So it has to increase as we go toward our resistor. There's no potential drop along the ideal wire, so the potential difference increases in the battery to 1.5 volts. No potential drop along the wire. It decreases by 1.5 volts in the resistor and becomes 0 again as we come back to the negative terminal. What this is showing us is this bit right here. This is the resistor part right here, and this is what we call voltage drop. So I wanted to show you this so you can kind of look at a visual when we start talking about voltage drop. We've got a little bit of a visual to come back to. So this portion of the graph is as our current travels through that resistor, drops off. Okay, so on to electrical energy and power. A voltage source, like a battery, contains potential energy, which, when it's discharged, when that potential energy is just discharged, it's converted to kinetic energy into in the electrons. Okay, the resistance of a circuit then converts that kinetic energy of the electrons to thermal energy. And we can see this whenever a light bulb, after it's been on for a little while, warms up. The circuit uses up the energy that's provided by the voltage source, converts that potential energy here into kinetic energy of the electrons, into the thermal energy in our circuit. Now, we know that the potential energy is this QV. We know that the rate at which the potential energy is provided is power. Okay, power is work over time, or work being the change of energy. Work is the change in energy over time. Then what this tells us is that our power is equal to the change in our electric potential energy over time. So we take this and we can put that there, and we end up with our power is equal to the QV over T. Now when we look at this, we can see right away that there's a bit of this Q over T, that looks really familiar. We've just seen this. It is current. So substituting in then the current for the QT, Q over T, we end up with power is equal to IV, where P is our power, I is our current, and V is our potential difference. And what this is going to give us, it'll give us the power that's dissipated by some resistor with a current going through it, and from some potential difference. Now, if we apply Ohm's law to this, we're going to be able to develop two other power equations that, there we go, we'll be able to use as we solve power questions. So, to start with, we've got P equals IV. There's our power, electrical power. Okay? And then we're going to apply then Ohm's law to this. Okay? So, the first thing that we see here is we have P equals IV and we have V equals IR. So we can take IR and put it in right over here, and we end up with P equals I times IR, simplified into P equals I squared R. Okay? So this is power equation number 2. Here's this power equation number 1. Here's power equation number 2. Okay? So clearly we'll be able to use power equation 2 when we don't know our potential difference and don't have any way to figure it out. We'll use this one when we don't know our resistance. Okay? So to look at the third one then, again we start with P equals IV and V equals IR. And this time let's go ahead and solve Ohm's law for current. We end up with the current is V over R. We can take that and put that into power equation 1. We end up with this VR over V, or rather times V. So we simplify this, and we can see that it's P equals V squared over R. So there we have the three power equations. We have P equals IV, P equals I squared R, and P equals V squared R, which we'll use depending on what information we're given and what we're looking for. Now, when you go to take the AP test, you're only going to be given this and Ohm's law right down there. So what you have to be able to do is derive these two from those. So then, example C on your notes says a car battery has an EMF of 12 volts. When the car's motor is running, the battery current is 320 amps. Okay, what power does our battery supply? Well, we got our power equation. We have we know we have a potential difference right here. That's our EMF. We have a current right here. We're looking for power. So we're going to use power equation number 1. So P equals IV, where we've got our 320 amps there. We got our potential difference of 12 volts. This ends up being 3.8 kilowatts. Okay? Great. So, next one then. We're asked how much current is drawn by a 100 watt light bulb. So we've got a power of 100-watt light bulb when it's connected to a potential difference of 120 volts. We plug the light bulb into the wall. This 100-watt light bulb, we want to know how much current is drawn for that. Again, P equals IV, 100 watts over 120 volts. We get a current of 0.83 amps there. Okay. In the next example then, it says how much power is dissipated. So we're looking for power. How much power is dissipated by a 60-watt light bulb when it's at 120 volts when operated using a dimmer switch at 100 volts. Okay? So what this is saying is we got this 60-watt light bulb, right? Now this 60-watt light bulb, when it's running at 120 volts, when it has a potential difference of 120 volts, it will produce a power of 60 watts. Okay. Now the thing is, this is a circuit element, and that's when we have this circuit element in there, because we're applying Ohm's law in with these power equations. The resistance of any circuit element does not change. Okay, the resistance won't change. So what we're going to want to do is we want to first find out what that resistance is, and then we'll be able to apply one of our other two power equations to figure out the power at 100 volts. Now, because we don't know anything about the current, we're going to want to use this expression for our power. So when we're at 120, we're at a 60-watt bulb, right? And when we're running that thing at 120 volts, we've got it completely cranked up. We want to figure out what its resistance is. Okay, we run through this. We get a resistance then of 240 ohms. Now that resistance is not going to change when we dim down our bulb. What we're changing when you dim down that bulb is you're changing that potential difference. Okay, so this time, again, we don't know anything about the current, so we're still going to use V squared over R. Now we have we want to know how much power are we getting out of our 60-watt bulb at 100 volts. So we put in that resistance we just figured, and we end up with power of 42 watts. Okay, which makes sense. We're running at a less potential difference, so we should have less power coming out of our 60-watt bulb. Okay, then our final example says most stereo speakers are designed to have a resistance of 8 ohms. So if an 8 ohm speaker is connected to a stereo amplifier with a rating of 100 watts, what is the maximum possible potential difference the amplifier can apply to the speakers? Okay, so when you see a resistance rating of an amplifier, it's the maximum power, or when you see the power rating of an amplifier, it's the maximum power that amplifier can deliver. Most of the time it delivers a lot less, but the maximum might be needed for brief, intense sounds. The maximum potential difference will occur when that amplifier is providing the maximum power. So we need to make we need to figure this out with that in mind. So we'll model our speaker then as a resistor. So the maximum potential difference occurs when the power is at a maximum. At the maximum power then of this 100 watts, we'll use this equation. Whoops. There we go. We'll use this equation. So we're operating at 100 watts. We want to know what our potential difference is when we've got 8 ohms. And we end up with a potential difference of 28 volts. Okay, so that is really leading us into circuits. The next lesson, we're going to be looking specifically at various circuits, series, parallel circuits, and the circuit rules and how to apply them. See you then.